All right, hello everyone. Today we are going to be talking about vibrations of a string, also known as standing waves. Our objectives for this lab are going to be to identify the fundamental mode of a fixed vibrating spring. From that fundamental mode, determine higher modes or harmonics, find the velocity of a standing wave, and discover the effect of tension on a standing wave. Now first, we need to talk about mechanical waves. What are mechanical waves? You can think of a mechanical wave as a disturbance that propagates through a medium. That's kind of how I think about it. You could have ripples on water, you could have sound in the air, or movements in a stretched slinky. So the two pictures here we have are an actual drop. You have some water, and you have the ripples that would move out from the center. And in the other picture, we have a longitudinal wave versus a transverse wave. The transverse waves are what we're dealing with. Longitudinal waves are more like how sound travels through the air. So what is a standing wave? A standing wave is one that has two endpoints that are bound, so they can't move on their own. Here we have this picture, we have somebody making a disturbance in the wave. It travels down and then reflects coming back. Here's a picture that shows the equivalent of what we're going to be doing, which is making waves that add up to each other. Notice that the wave has boundaries at both ends, so it reflects and then adds to itself. Now, when something adds, remember we call that superposition. Now, superposition is, of course, the property where things can add together, kind of like how forces can add together. They can superimpose on each other. Well, whenever the waves add together, you get a certain pattern. Whenever this pattern makes a certain design, then you know that you've hit a harmonic. So this little picture shows how a wave travels down a string and then reflects. Notice it's on the top side going in and then the bottom side going back out. So when the incoming waves add the reflected wave, you get, when it adds to the reflected wave, you get constructive and destructive interference. Constructive interference is when things add together to make something bigger. Destructive interference is when things add together to nothing. So here we have some constructive and destructive interference. Whenever the line is straight, everything is in destructive mode. And then whenever you have the peaks, that's constructive. And then you notice the areas where they don't, where the string stays in the same place, it doesn't really move. That's areas of destructive interference. And so whenever they add together and constructively, we get antinodes, and when they add together destructively, we get nodes. Okay, now harmonics. Harmonics are what we're going to be dealing with. Harmonics are when things add together, and you get this nice little pattern, which means that the nodes end up at the ends of the string. So there are two equations here that you definitely are going to want to know. Lambda, which is, of course, the wavelength, equals 2L over N. N being the number of the harmonic, and L being the string length. Now, Fn equals V over lambda. Now, F is the frequency, V is the velocity of the wave, and then F, okay, say frequency of the vibration. V is the velocity of the wave, and lambda, of course, is the wavelength. Okay, now we're going to talk about the mass, tension, and velocity relation. The velocity of the wave is going to be equal to the square root of the tension over the mass density. Now here we're talking about linear mass density, where it's a mass per unit length. You may be familiar with regular density, which is a volume density, which is a mass per unit volume. Well, this is very similar, but instead of a volume, we're going to go one-dimensional and take a line density. And that's going to be in units of kilograms per meter, grams per centimeter, so it's going to be a mass per unit's length. Of course, tau is tension and v is velocity. Those two things I hope that you understand by now. Okay, now this is how the experiment's going to go, kind of, your workflow. You're going to measure the string length and find the needed harmonic, and that will be, you need to find the first harmonic, second harmonic, third harmonic, fourth, fifth, sixth harmonic, and then find the wavelength. Now from that, hint, yes, it is easier to find the second harmonic than the first harmonic. The first harmonic is really, it's hard to see one string bounce back and forth and make sure that the nodes are at the end. So what you do is you look for the second harmonic. That is very well defined. You'll be able to see it, and you'll know when you hit it. And the first harmonic should be about half of that. So then we're going to use the frequency and the wavelength. So you found the frequency, you've calculated the wavelength. Now you're going to find the velocity of the wave. And then you're going to use this velocity, and then you'll need to calculate the tension to find the linear mass, mu, of the string. And then you'll need to verify your findings. We'll have a known sample that is of a specific length, and you're going to measure it to find out what the mass per unit length is, and is that what you calculated? How close are you? What percentage off are you? Are you going to be able to hit it dead on? And where could things have gone wrong in the experiment? Okay, well, that is pretty much all I have for today's lecture. So I look forward to seeing you guys in class. Talk to you later. Bye-bye.